Welcome to the next lecture of FPGA module. In this part of the module, we will be mainly focused on the practical aspects. However, before we start the lab, I have to provide you some necessary theoretical background information that we will go through. And I think before lunch, we should be able to finish with theory. And ideally, we would like you to start the first lab out of 3. Please make sure you have the lab sheet for the first lab. While we are going through the theory, please make sure you have Vivado and other related software installed. Please feel free to talk to Harsh and Deepak, who are sitting here. I think we can parallelize this, so you can go to them and ask for advice while we are going through the theoretical material, so that we can start practical session on time. We do understand that it's not that straightforward to install all those applications, so we encourage you to work in groups. If you have one working laptop machine, that is fine, because anyway the main bottleneck is the number of Z boards rather than a number of laptops. So please cooperate with each other. And I think we are ready to start with theory. So before we go to FPGA part, we would like to start with CPUs, which is a kind of reference point which we are familiar with. So keeping in mind the model that Eric has proposed in the previous session, so we have regardless of the architecture, we have computing subsystem, memory subsystem, and communication subsystem. So if you consider the standard CPU architecture, if you try to look with a microscope inside the chip, so what you will see, one of the main components is arithmetic logic unit. So this is, as the name suggests, this is the unit that performs arithmetic and logic operations. This could be simple operations like AND gate, addition, or maybe some more sophisticated operations like floating point division or square root operation, things like this. So you have a ALU, arithmetic logic unit, that is connected to registers to store inputs and to a register to calculate output. In addition to processing subsystem, we have memory subsystem, which is partially located outside the chip, but mainly it is inside CPU. So we have the whole hierarchy starting from registers. Register is another way of saying flip-flop. So it's a tiny piece of circuit that holds 1 bit of information. So we start from registers, then we have certain layers of cache, and we end up with external random access memory. Depending on the technology, this memory is implemented. This could be called DDR, DDR2, 3, DRAM. So there are different types of memories, but the common thing is that they always sit outside the chip, and this memory is energy dependent. So if you don't supply energy, all the data will be lost. But the main thing to remember is that there is always a trade-off between capacity of that memory block and the access time. So for external memory, we usually don't have any practical limitations in terms of capacity. So today's computer might have 64 bits of memory. That is not that expensive. Then we have another layer of cache, which is less capable in terms of amount of data it can store, but it is faster. And the fastest memory is flip-flop register. So you can access data within 1 clock cycle. So you access it, immediately process it, and storing data back usually takes 0 clock cycles because processing and storing happens together. Okay, so imagine you have 2 numbers in your memory and you want to add them together. So what normally would happen, you have to these 2 pieces of data have to travel through the entire memory hierarchy before it can be actually processed. So we go from RAM to cache, from cache to registers, and we might have more than 1 layer of cache, L1, L2 cache memories. So then we do actual computation, and after that we have to store this back. So we see most of the time, as we have seen in the previous exercise, most of the time data is just traveling and no computations are happening. Okay, yeah, the alternative is using FPGAs. So as the name suggests, we have an array of logic blocks. So one logic block, this could be lookup table, flip-flop, or maybe something more specific like DSP or BRAM. And these blocks, they are connected via switch matrices. So these tiny black rectangles, these are switching matrices. And the main goal of FPGA designer is configuring those switch matrices. So by configuring these switch matrices, in theory, using FPGA, we can build a standard processor. But in practice, we would like to build something more sophisticated, like something more tailored for our application, like adder tree, or maybe we have some other specific operations that do not map efficiently on the set of operations that we have, but it can be more suitable for FPGA implementation. Before we finish with CPUs, just a small remark that this is a general architecture. So the same architecture applies for CPU, for GPU, for PLCs. The only difference comes from the way how ALU is implemented, how many operations does it support, how complex that operations are, how many levels of cache. So maybe you have several ALUs with local cache and common shared memory. So these are application-specific features, but the general concept is still the same. So you have memory hierarchy, you have processing system, and something that is not shown here is communication. So you have to move data between memory layers in order to perform computations. Okay, so coming back to the same example of adding two numbers, what we can do with FPGA, we can synthesize. So we use BRAMs, BRAMs to synthesize memory. Let's say we know in advance that we want to add two vectors of a certain length. We know in advance, and we synthesize memory with respect to that requirements. Note that with CPU we might have large memory with few numbers, so we simply lose all that silicon for nothing. Okay, and in this case, how pipelining would look like. So it will go like this. So reading also takes one clock cycle. Let's say one clock cycle is adding, and then there is a stream that goes very similar to what we did before. In addition to pipelining, we can also partition memory blocks. So we are not restricted by memory. So we can have multiple small memory blocks or one large memory. So it's up to us. So we partition memory, and then we replicate computational units and do computations faster. In this case, we don't have any dependencies, and it is likely that we will end up with a design which is twice faster than pipeline design without any parallelization. Yeah, and now the question is, how do we, okay, we know that we are flexible, but how do we exploit this flexibility? So how do we configure these switch matrices, these tiny matrices? The main designer's goal is to figure out what is that bit stream that describes connections within that switch matrices. But obviously we will not do this on bit level. So we will use some higher level languages that allow us configuring these matrices. What we do in software, we normally define a set of commands. So let's say you want to do this operation. So we multiply two numbers, divide another two numbers, and add the result. And this is what we do in software. So we load these two operands, we do multiplication, store the temporary result, load another two numbers, do division, store temporary numbers, and then finally we do addition and store it back. So memory operations are highlighted with bold font. So we see most of the time we spend, most of the commands are related to to data transfer. With the reconfigurable approach, what we would normally do, we will synthesize registers. So these are flip-flops. So throughout this talk, I will use registers and flip-flops interchangeably. So this is essentially the same thing for our application. And we physically synthesize required units, and we build a tree. So it's not homogeneous that it was the case previously. So we have different units, but still the principle is the same. We have different units, and we can implement flow. So also we can, in case we have vector operation, we can pipeline these operations, and this is the circuit that we would build for that. The one thing that I don't show here, and it's a standard convention for FPGA community, we don't explicitly show flip-flops between the blocks. So it is assumed that operation itself might have several stages. So multiplication is normally not one clock cycle. So we have internal memory blocks inside each computational unit, and we have memory blocks, registers between them. But in practice, we don't show that, and it is implied. And plus, we have to take into account that division might take longer than multiplication. Then we might end up with inserting additional redundant flip-flops to ensure that these two operations, they are synchronized. So to ensure that adder receives two pieces of data at the same time. Okay, and we remember that we have some physics behind these blocks. So by physics, I mean some mechanical, electronical system. So we can use something really physical, something mechanical. This is slightly more sophisticated approach. So you have this calculator. Still, you need to spend energy to rotate the handle. And I think in this case, you would rather calculate it yourself rather than rotating this handle. But nowadays, what we have, instead of using these mechanical calculators, we mainly rely on transistors. But before we move to transistors, I will give a quick overview of other computer types that we have. So some of them are really hobby projects. So I will upload this presentation on the web page. So domino computer, this is literally made of domino blocks. So if you put them in a sequence, so they mimic current behavior. I suggest you have a look here. This is not a practical computer. I think they implemented 4-bit adder. This is something that we will do in the second lab. Relay computer is the next stage. It's much more efficient than domino, but it's not really fast. And the last 2 points, this is ongoing research. They use different physical principles, but I suggest you go and have a look. But between mechanical approach and quantum computers, we are sitting somewhere here. We use transistors. So this is what is happening today. So let's say we have a certain operation that we want to implement. Let's say it's NOR AND, and we can use transistors in order to implement this circuit. So this is based on MOSFET transistors. So the main idea is that the signal is voltage, not current. This allows saving energy because current flow requires energy, but voltage is just like pressure, so there is no flow. But still, there is some leakage current, and that is why processors consume energy. But practically, we have billions of transistors in a single chip in order to build architecture that we need. So this is, I think that is an Intel processor with 4 cores and shared cache memory. But we are focused on something that is not given to us. So we are focused on FPGAs. So in contrast to fixed architecture, there is nothing inside. And our goal is to build this architecture. Instead of telling what to do, instead of telling existing architecture what to do, we will be telling FPGA what to be. So what do we want it to be? And to do this, we will use several hardware description languages. And similarly to CPU, we have a trade-off between level of abstraction on the one side and efficiency of the final implementation on the other. Okay, so the highest level okay, I think we'll start from the lowest approach. The lowest approach is schematic design, which essentially means that with schematic design we have certain graphical environment. It is similar to Simulink, and what we do, we connect these logic blocks manually, and every wire on this graph represents one voltage. So every wire carries voltage, so it's one voltage signal. And you can imagine how unscalable this approach is, especially taking into account the fact that today's chips, they have billions of transistors, and in practice it is not possible to manage this project. That is why in the, I think, late 80s there was a new approach proposed by Pentagon. So what they proposed, that was VHDL, which today VHDL is mostly used in academia, and another HDL, Verilog, it is more industrial language. So we will use VHDL in our labs. So so I will not go into details of HDL at the moment, because we will cover this in the first two labs. So the main idea of HDL is that you are describing your circuit using code instead of doing this graphically. In this case, you can do code generation, you can connect these blocks easily, you can automate the design process, and this gives you some other benefits. Going further with the level of abstraction, we end up with high-level languages. In relation to FPGA, we normally say high-level synthesis. Yeah, by the way, for software we say compilation, so we compile code to get assembly code. In FPGA we synthesize circuit, but sometimes we also use compiling circuit, but mostly we say synthesis. So here we would say high-level synthesis. Today we have several languages. Most of them are based on C and System C. Still, you can't go easily to Python level. In theory, there are some languages. Again, this is trading off design time and circuit efficiency. But again, normally what happens when you use HLS, HLS generates HDL code, and then this HDL code goes to the vendor's software tool. So this can be considered as a wrapper around HDL. And the highest level approach is using model-based languages. I think the most popular example would be National Instruments VHDL module. They provide you both software and hardware. Although their hardware is also based on Xilinx tools, they provide a nice wrapper so that you can use FPGA from high-level environment, LabVIEW. The same applies for MathWorks with the MATLAB HDL coder. The only difference is that MATLAB does not provide hardware, so they assume using these development boards like Z-board that we will be using today. This can be considered as advantage or disadvantage, because on the one hand you don't have any guarantees of compatibility of your software and hardware, but on the other hand you can target a wide range of hardware platforms. So normally on the first glance it might look like schematic approach, the one that we considered in the beginning, but with the LabVIEW or Simulink approach, one block is a complete component, and you often have libraries of these components, but most of these libraries, apart from simple addition and multiplication operations, they are tailored for signal and image processing applications. So you will find something like fast Fourier transform block, maybe matrix vector multiplication block, some FIR, IR filters. So you connect them, and you can deploy, you can synthesize your circuit and deploy your algorithm on hardware right from the Simulink environment. Again, today we are focused on these two languages, so we will be using VHDL in the beginning. That will be very simple circuits, just to give an impression to what circuit synthesis is. And then we will move to high-level synthesis. Again, we will be using Xilinx vendor's high-level synthesis tool, known as the Vivado HLS, and we will be using C for that.